Hello there, Mr. Sutton here, bringing you the AB Calculus 6-3 Extra Practice number 4 solutions on slope fields. For this problem, they want to know which of these differential equations matches the slope field up here. So I'm just going to check out a few values on this slope field and see if the x and the y values there give me the same answer in these different differential equations. So let me check out 0, 0. Looking that up in the slope field, that appears to have a slope of 0 if I have to estimate it there. I mean, we're getting less and less steep until we get there, so that's most likely a slope of 0. So now testing that out in my different answer choices, if I plug in 0 for both x and y, well, there's only y values for all of these, so that's kind of interesting. This first one gives me 0. This next one, b, gives me -1. So I can actually eliminate that. That's not a slope of 0. This next one gives me 0, and choice D also gives me 0. Okay, so let me test out something that doesn't have 0 for both numbers. Let me make the x value 0, but let me make the y value different. So let me try 0, 1. If I look that up in the graph, that's another easy one to look up. At 0, 1, we have a slope of 0 again. So now testing that out, choice B, remember, was eliminated, but let's go to choice A. At 0, 1, this is now going to be 1 squared, which is 1, not 0. So choice A can be eliminated. Down to choice C, this is now going to be 1 squared plus 1, which is going to be not 0. It's going to be 2. So choice C is also no good anymore. And choice D, just to make sure I didn't throw out the baby with the bathwater, as they say, this would be 1 squared minus 1, which is 0, which is what we were expecting. So then choice D. On this problem, I'm trying to match one of these differential equations with this slope field. So we're basically going to use process of elimination. I'm going to test out a few values in the slope field to see what slope it gives me and see if the differential equations at those x and y values give me the same numbers. So the first one I always like to test out is 0, 0, which in the slope field, we have a horizontal tangent line there, so we should get a slope of 0 if I plug in 0 and 0 in the differential equations. But now if you look at all of these differential equations, the way they're set up, if you plug in 0 for x and y, they all give you 0 back, so that wouldn't actually eliminate anything. So I'm going to need to make one of my values not be 0. Let me try 0 and 1. Let me try 1, 0 actually. So that's right here on the slope field. That is also a slope of 0. So now plugging in 1 for x and 0 for y, let's see what that gives us. Choice A, that would give us 1 plus 0, which is not 0, so we can eliminate A. Choice B, we would end up with 1 cubed, which is also not 0. So B is gone, so this is good. We're down to C and D. C, we would have 0 cubed, which is 0. D, we would have 0 squared, which is 0. So we have to choose between C and D. At this point, since it's really just a difference of an odd versus an even exponent, I'm going to be a little bit clever about my next choice, and I'm going to pick a negative y value. That should help me tell the difference between these two differential equations. So let me not overcomplicate things. Let me pick the point 0, -1. So that's this point right down here. Now, I don't know exactly what that slope is, but I can tell that it's at least positive, which should be enough to tell the difference between C and D. So if I plug -1 in for y here, C gives me a negative slope, which is not what I wanted. If I plug in -1 to option D, I get a positive slope because I'm squaring. So choice D then is the only one that is still going to make any sense. For this problem, I'm trying to figure out which slope field could represent this differential equation. So the way I'm going to do this is I'm going to pick an x and a y value and plug them into this differential equation, see what slope I get, and then I'm going to compare that with the slope at that point on each slope field. So, I mean, my favorite one to pick is always 0, 0. That would give us a slope of 0 if we plugged it in here. But if you look at all these slope fields, it looks like at the origin, all of them seem to have a slope that could be argued to be 0. I mean, they didn't give us an exact tangent line there, but those all look like they could be 0. So 0, 0 doesn't help as much. So what I'm going to do, maybe I pick a different x and a y value. Let me test out, for example, either 1, -1 or -1, 1. Let me go with -1, 1. So negative x value, positive y value. That would still give me 0, because you're basically doing 1 minus 1 in that case. But now let's see which of these slope fields has a slope of 0 at negative 1, comma 1. So taking a look at choice A at negative 1, 1, that is definitely a positive slope. There's no way that is 0. So A can be eliminated. Choice B at negative 1, 1, well, I'd say that's debatable. It might be a little negative, a little positive. It might be 0. I can't really eliminate B based off of that yet. So let me see if I can at least eliminate the other ones. Choice C at negative 1, comma 1, that is absolutely not a slope of 0. That's a positive slope, so C is gone for sure. And choice D at negative 1, comma 1, that is also definitely not 0. So based off of all of these, I can absolutely eliminate A, C, and D. Cannot eliminate B, so by process of elimination, it's got to be B. For this problem, I'm trying to figure out which of these differential equations goes with the slope field given above here. So the way I like to do these is just pick a value on the slope field, see what the x and the y actually give me for a slope, and then see if that same x and y value give me the same slope in the differential equations. Easiest one to test out is 0, 0. On the graph here, 0, 0 appears to have a slope value of 0, horizontal tangent line there, or at least that's what it should be based on the directions these things seem to be going. But the problem is, if you plug in 0 and 0 for x and y, in all of these differential equations, they're all going to give you 0 back. So that's actually not helpful at all. What would be helpful, though, is maybe if we had a different x and a y value, that could help us tell the difference between these. So let me try out 0, comma 1 instead. So 0 for x, 1 for y. Looking that up in my slope field at 0, comma 1 right here, we still seem to have a slope of 0. So that's still pretty easy to pick out from our graph. But now if I plug in 0 and 1 in all of these, so this is 0 squared plus 1 squared, which is not going to be 0. It's going to be 1. So choice A can be eliminated. Choice B, we have 0 squared times 1 squared, which comes out to 0. So we can't eliminate B just yet. Choice C, we have 0 squared minus 1 squared. That's negative, so that's not going to work. C can be eliminated. And now choice D, well, this only takes the y value, so this is just 1 squared, which also does not come out to 0. So we can also eliminate choice D. So with that 1 point, we're able to eliminate 3 out of the 4, so that must mean that choice B is the answer. For this free response problem, we have, let's see, the differential equation 1/3 x times y minus 2 quantity squared. And our first task, given this slope field for our differential equation, we just have to sketch a solution curve that goes through 0, 2, and another solution curve that goes through 1, comma 0. So let's do the 0, 2, 1. So that means we have to go through this dot right here. And they put the dot on there for us, which was awfully nice of them, but I'm going to put a bigger dot. I like my dot better. So we have to follow the tangent lines and go through this dot. This is on a series of horizontal tangent lines, so this is just going to be this horizontal line right here. No need to overcomplicate things. Now at 1, comma 0, that's this dot down here. This one is part of something a little more complicated. So if you look as we go to the right, we're following the tangent lines kind of this way, and to the left, we're going down and then seeming to kind of bounce back up in this kind of a fashion. So it's not quite a parabola because there's some inflection going on, but it's something parabola-ish looking. Something a little bit like this if you're following these tangent lines. For this problem, y equals f of x is the particular solution to this thing with an initial condition of 1, comma 0. For this part, we just want the equation of the tangent line to this, to y equals f of x at x equals 1, and then approximate f of 0.7 with it. So in general, tangent line has a setup of f of a plus f prime of a times x minus a, where a is just the x value that they're giving you a point for. So in this case, we want basically f of 1 plus f prime of 1 times x minus 1. What's f of 1? Well, they told us that. It's 0, so that was pretty easy. F prime of 1, we're going to have to use the differential equation to find that. So when I do f prime of 1, I'm plugging in the x value 1, and I'm also plugging in the y value that goes with 1. So we're going to have 1/3 times the x value 1. But now we're going to have the y value 0 because that's the point, that's the part of the point that has the x value 1. The y value is 0 minus 2 squared. And what does all that come out to? Well, let's see. This is negative 2 squared, which is 4. This is, let's see, 4 times 1 is still 4. 4 times 1/3 is 4/3. So we have plus 4/3 here. And then we still have x minus 1. So 0 plus 4/3 times x minus 1, y equals that. That is our tangent line that they asked for. Now we have to actually use that to approximate f of 0.7. So I'm going to say f of 0.7 is approximately equal to, we don't have to put the 0 out in front, so I'm just going to write 4/3, 0.7 minus 1. And I could stop here because these are all constants. I don't have to simplify. But if I do simplify, this is really, let's see here, this is like 7/10 minus 1, which is negative 3/10. And then if I multiply that by 4/3, these 3's are going to cancel. We have negative 4 over 10, which we could reduce to negative 2/5 if we wanted to, or negative 0.4. That also works. On the final part of this problem, they want us to find the particular solution to this differential equation given our initial condition here. So the key on these, you always have to check to see if you need to separate your variables. And the way we can always tell that is if the output variable, y, is in the differential equation. Now we see that y is in this differential equation on this problem. So that tells us, hey, we got to separate variables here. So let me do that by dividing both sides by y minus 2 squared. That'll give me y minus 2 to the negative 2 on the left side then to go with the dy. And then the dx needs to be somewhere else. So we're going to multiply it over to the right side, giving us 1/3 x dx. Taking my antiderivatives now, on the left side, this bumps up to a negative 1. So I have negative 1 y minus 2 to the negative 1. And on the right side, using my reverse power rule, this bumps up to a 2. Dividing by that, we have 1 over 6 x squared. And don't forget the plus c, because we need that on the next step. To find that c value, we're going to plug in our initial condition of 1, 0. So I've got negative, let's see, y value is 0, minus 2 to the negative 1. And on the right side, this is 1/6 times the x value 1 squared plus c. So let's see here. This is 1 over 6 plus c on the right side. On the left side, this is going to be, let's see here, we have negative 2. Raising that to the negative 1 power, that's negative 1/2. But we have a negative out here, so that's positive 1/2. So when the dust settles, to get c, I need to do 1/2 minus 1 over 6. Well, that's really 3 over 6 minus 1 over 6, which is 2 over 6, which is 1 over 3. So 1/2 minus 1 over 6 gives me 1/3. So there's my c value. I can now plug that in up here for this c. And now I'm going to start isolating y, which is what I always need to do to call these problems done. So let me start by multiplying everything or dividing everything by negative 1. So we have negative 1 over 6 x squared plus or minus 1/3. Actually, before I even do that, let me turn this into one big fraction. And the reason I'm going the one big fraction route on this is I see that I have this negative 1 power I'm going to have to get rid of. So that means I'm going to have to take the reciprocal of both sides, which is a lot easier if you just have a single fraction on one side. So let's see here. We have a common denominator of 6. This is really x squared plus 2, everything over 6. And now let me multiply both sides by negative 1. So that just makes this fraction over here negative. To get rid of the negative 1 power, I just take the reciprocal of both sides. So I have y minus 2 equals basically this fraction upside down. And then finally just add 2 to get y completely by itself. So a whole bunch of algebra. At the end of the day, there is our final answer.